Hello to you all. Thank you for joining me on today's lesson. This week we'll be looking at matrices. But before we go into matrices, we'll just take a brief definition on what vectors are. So we are saying physical quantities can be divided into two main groups. We have the scalar quantities and the vector quantities. And we are saying that the scalar quantity is one that is defined completely by a single number with appropriate units. Examples are, you could have length, area, volume, etc. Talking about mass, time. Once the units are stated, the quantity is denoted entirely by its size or magnitude. Then when we talk about a vector quantity, we are saying that it is also one that is completely defined when we know not only its magnitude, that's the units we're talking about for the scalar parts, but also the direction in which we operate. Take for an example a force. A force does not only give you the magnitude, the units, but you know the direction in which you are going as well. Same with velocity and other quantities like acceleration as well. That we say a vector quantity has what we call the magnitude and direction. An example, we are saying the weight of 8 kilogram mass is what a scalar quantity. It's just the weight of an object. So it's a scalar quantity. But let's talk about an acceleration of 9.8 meters per second vertically downwards is a vector quantity. So you have the magnitude, the unit which is given, and vertically downwards is giving you the direction. So we say acceleration is an example of a vector unit. How do we represent a vector? We are saying that a vector quantity is graphically represented by a line. So you have a line. So this is a line such that the length of the line denotes the magnitude of the quantity. So I have a line here, A to B. The length from A to B would denote the magnitude, and the direction of the line denotes the direction in which the vector quantity acts. So we have a direction here, this arrow representing the direction. So the arrow actually gives us the direction we are looking at, whether it is going in this direction as you are seeing. So the vector quantity AB is referred to as AB, or you can write it as what? In a bolder space, A. As we move on and do higher math in physics, you would see different notation for a vector. So don't be bothered when you see things like that. Okay, so there are some vectors in Cartesian coordinates. So you have vectors in different dimensions. So we have the 2 dimensions. That's our x and y direction. So the x direction we are represented by I hat. Then the j dimension we are representing, the y dimension we are representing by j hat. These are what we normally call the unit vectors. Unit vectors. So you see different types of vectors as we talk about the dimensions and the coordinate system. So in 2 dimensions, the unit vectors in the directions of the 2 coordinate axes are written as I and j, which I previously mentioned. That is a unit vectors. So if a point P has coordinates x and y, then the position vector OP may be written as a combination of these 2 unit vectors. So one type of a vector is what we are calling the position vector. So if you take these 2 dimensions, so we are saying from O to P is a position vector, and normally the position vector has a fixed what? O. So O is always fixed. Then to the point what? P. So this is what we are calling what? A position vector. Okay, so with this position vector, it can be written as a combination of its unit vectors. So in the direction of x, I plus y what? J. Or equivalently as a column vector, OP can be written as what? In this column form, x and what? Y. If you take 3 dimensions and we are looking at the x, y, and z direction, so you have a coordinates in x, y, z. So in 3 dimensions, now we've extended the unit vectors, so we now have I, j, and k. If a point P has coordinates x, y, j, then we are saying that the vector OP, the position vector OP in 3 dimensions can be written as xi plus yj plus what? Z what? K. And equivalently in a column vector form, you can write it as this. Very good. So now let's look at the length of a vector, a position vector. So I have a vector in a 3-dimensional. In 3 dimension, I want to find the length of the position vector, that is OP. That is the length I'm looking for. How do I go about it? Okay, so we are saying if P is a point with coordinates x, y, and z, and the length or magnitude of the position vector is given by the formula this. So this is the magnitude. That is square root of x squared plus y squared plus z squared. So when you hear length or magnitude, it means the same thing. Nothing has changed. So length and magnitude. So if you are asked to find the magnitude of a vector given, if it's 2 dimension, then we just have x squared plus y squared. But if it is in 3 dimension, then we have x squared, square root of x squared plus y squared plus z squared. The angle between a position vector and an axis. So we want to look at a position vector. We still have our position vector OP. We want to find an angle, the angle between that position vector. How do I go about it? So let's say this is the state I'm in, a 3-dimensional coordinate system. I have my vector O. I have the position O, P, and A here. So virtually this is, I want to find this angle alpha. How do I go about it? Okay. So we are saying the direction between a position vector and an axis. The direction cosines of the points P describe the angles between the position vector OP and the 3 axes. If P has coordinates this, then the direction cosines are given by, so cosine of alpha, you can write it as this, cos beta as that, cos gamma, it's z over square root, that's over the magnitude. Okay, so the direction cosines of any point P satisfy this, that's if I add this, it should be equal to what? 1. So a unit vector in the same direction as the position vector OP is given by this expression. This expression we are seeing here. Okay, vector algebra. So just like we do algebra in real numbers, you could add 1 plus 2, multiply and subtract. We could do the same thing for vectors. So if we have a vector A, we can multiply it by a scalar. So I have a vector A multiplied by this, so the result is a vector B, this, which has a magnitude this. Okay, so B equal to the magnitude of what? AB. So the scalar gives you the ratios of what? A vector. So a vector B is parallel to A. If you look at these vectors, and we are saying that the vector B is parallel to A and points in the same direction if A, the scalar quantity we are looking at is what? Greater than 0. But if we have a scalar quantity we are multiplying by the vector, then you realize because it's less than 0, then it becomes negative. So it moves in the opposite what? Direction. So this is my initial vector A. Depending on the scalar I multiply, it can increase the magnitude of the vector. So if A is greater than 0, then it's going to increase the magnitude. So let's say I multiply this by 2, then it means I have 2 of that. So you have another the vector extended. If the scalar quantity I have is less than 0, then it's going to be a negative vector. So it's going to, the direction is going to what? Change. It's going to be the same vector, but the direction is going to be in the opposite form. Then addition. So if I have this coordinate system, I can find C by adding the vectors. So I have vector C to be equal to A plus what? B, or B plus A. So this commutative property is here. You can also find the associative property as well. That's a vector A plus B plus C. You can write it as A plus B plus C. Then subtraction as well. So we are saying if we have this coordinate system, this is our vector A, this is our vector B. The opposite direction of this is what? B will be what? Minus B. Okay. So if I want to add the two vectors A, so I could add A plus B. This minus B. So A minus B is the same as A plus this vector, which gives you this. So A plus minus B is this vector in that direction. Don't forget the direction as well. Okay. So we are saying since A minus B is equal to A plus minus B, in order to subtract B from A, we simply multiply B by minus 1. Then we do what? We add. Okay, so then we move on to our matrices, which is the main topic for discussion. So we are saying a matrix is a rectangular array of complex numbers. It could be real numbers. So the numbers are called elements or entities of the matrix. So a matrix is often denoted by uppercase letter, let's say A. The elements of the matrix A located in the ith row in the jth column is denoted by Aij, A subscript Ij, which may be written as this. So the Aij, A represents the matrix we are looking at. Then our I and J, the I is the row and J is the column. Thank you so much. We'll continue with our matrix in our next lesson.